Yeah? We are starting now. How much we did, can you remember? Kamjit? Hello?
Hello, sir. I think so. Today we should start Half-Life.
Half-Life, okay. Half-Life we did not do, right? Before Half-Life we did everything. So before Half-Life, what we did?
We did Life of Stars. We did nuclear fusion.
Nuclear
And
fusion.
yes.
And before that, what we did?
And before that, we did nuclear reactor.
Nuclear fission, right?
No, nuclear reactor.
Nuclear reactor. And before nuclear reactor, nuclear fission. And before nuclear fission?
It was alpha, beta, and gamma decay.
The difference between nuclear reaction and chemical reaction. And before that, the characteristics of alpha, beta, gamma. And before that?
Before that, Fleming's left-hand rule.
Fleming's left-hand rule, it was the last part of alpha, beta, gammas, the deflection of alpha, beta, gamma in the magnetic field. That one was Fleming's left-hand rule, right? And before the three emissions characteristics, we had radioactivity, right? What is radioactivity? We had detectors, right? Different kinds of detectors. Then origin of radioactivity. So all these things we did. Only we left half-life. Then after half-life we have background radiation.
Oh.
Background radiation. Then we have finally carbon-14 dating, right? Carbon dating. Okay, what you are seeing? It's background radiation. Background radiation. Then before background radiation, we have half-life, huh? Here is half-life. So half-life means it is the time, huh?
This is the time.
Yeah, it is related to time, half-life. It is the time required to become the radioactivity of a sample to become half. Okay, like you are getting the radioactivity now, 1000 in your Geiger molar cube. You are getting the count now 1000. Then the time required to become the reading 500. That time is called half-life.
That much time is called half-life.
Okay. So why this happens? the reading is becoming half because the sample we gave, we are,
Hmm.
for example, given, for example, we gave the amount of uranium sample, it is
Hmm.
2 grams. So
Hmm.
after some time, it will become 1 gram, right? The sample of uranium will become 1 gram.
Hmm. Hmm.
So that time the emission will be also half. It was 1000, now it will become 500, right?
Hmm.
We know by emissions the nucleus changed, right?
Hmm.
And when it is changing the nucleus, it's no more uranium,
Hmm.
right? In 1 gram, there might be thousands of millions of uranium atom, right?
Hmm.
So 2 gram, there will be double.
Hmm.
So double of the uranium, the way they are emitting alpha, beta, and gamma, half of the uranium they will emit half, right?
Hmm.
Half emissions. So this way, we can say that the time required to become the number of nuclei from
Hmm.
its beginning, it's becoming now half. That
Hmm.
time is called half life.
Hmm.
Okay, now we are going to discuss that one. You have the some discussions here. Can you read please in radioactivity part? Yeah, from there half life in radioactivity.
In radioactivity, the internal of time required for one half
Interval,
of the
interval.
the interval of time required for one half of the atomic nuclei of a radioactive sample to decay into other nuclear species by emitting particles and energy, or equivalently the time interval required for the number of disintegration per second of radioactive material to decrease by one half.
Okay, so here in this paragraph, you got uh, two definitions of half life, right? The way I said, one
Hmm.
definition is related to the number of disintegration become half, right? That one I
Hmm.
said you that the number of readings or counting you are getting in the Geiger-Müller cube, right? If
Hmm.
the number of emissions is more, then you are getting more reading in the Geiger-Müller cube, right?
Hmm.
Yeah. So this emission is called disintegrations.
Hmm.
Is it clear?
Hmm.
Emission of alpha, beta, and gamma radiation, alpha, beta particle, and gamma radiation. This one is called disintegrations per second.
Hmm.
And another one is we have the number of nuclei, right?
Hmm.
The given sample, the number of nuclei available, the time required to become number of nuclei half,
Hmm.
or the mass of the sample become half. The same thing, right? The
Hmm.
number of nuclei is becoming half. That means the sample will also, if you consider with gram, uh, like you are given 50 gram at the beginning, now it's becoming 25 gram. So
Hmm.
why it's becoming 25 gram? Because the nucleus they changed, right?
Hmm.
That's why there is no more the given sample available. The sample changed to other nuclei. It was given uranium, now it's becoming cesium, radium, and other. elements, right?
Hmm.
Is it clear?
Uh, Kinda.
Okay.
Sir,
Like
wait. Like,
here,
why does it like give out radiation? Why is it changing the mass? Like, why it
okay,
is becoming half?
okay, very good. Thank you for your question. It's becoming half actually. For example, you are given 50 gram of uranium at the beginning, right?
Hmm.
So, what is the property of the uranium? Its property is that its nucleus is radioactive, right?
Hmm.
Because of this radioactivity, its nucleus will break down automatically, right?
Hmm.
It will convert to other elements when it will break down. Is it
Hmm.
clear?
Hmm. So
So
it's property.
yeah, its property. So it's not only property of uranium, polonium, then plutonium, all these radioactive particles, they show this property. Even carbon 14, it is also showing this. Because
Hmm.
why it's showing this property? Because of the uh, number of proton and neutron ratio is different, right? In
Hmm.
carbon, in carbon 12, you have six protons and six neutrons. That's why it's normal. It's not radioactive. But in carbon 14, we have six protons and eight neutrons. That's why it is
Hmm.
radioactive. It will spontaneously, naturally, it will decay. Alpha emission, beta emission, these things they will decay. Is it clear?
Hmm.
So by decaying, it's I am giving you example of carbon 14 now. By decaying, it's turning to nitrogen.
Hmm.
When it's emitting one beta particle, then it's turning
Hmm.
to nitrogen, right? So
Hmm.
in the beginning, in the sample, uh, we got here 50 gram of carbon 14. Now after half life, we are not getting in that sample anymore carbon 14 50 gram.
Hmm.
We are getting carbon 14 50, half of 50 is 25 5 grams, right?
Hmm. Hmm.
So other half is converting to nitrogen. We have still 50 gram there. If you take the whole thing like nitrogen and carbon 14
Carbon.
together, if you take the mass, it is 50 gram there. But uh, carbon 14 turns to nitrogen 25 gram and rest 25 gram is still carbon 14. Is it clear now?
Hmm. Hmm.
Is it clear?
Yes. Yes. Hmm.
Still, it is kind of, or it is clear, completely clear.
No, completely clear.
Okay, very good. Now it will be more clear to you. I am giving here another example. Can you continue reading?
Hmm. The radioactive isotope cobalt 60, which is used for radiotherapy, has, for example, a half-life of 5.26 years. Thus, after that interval, a sample originally containing 8 gram of cobalt 60 would contain only 4 gram of cobalt 60 and would emit only half as much radiation. After another interval of 5.26 years, the sample would contain only 2 grams of cobalt 60. Neither the volume nor the mass of the original sample visibly decreases. However, because the unstable cobalt 60 nuclei decay into stable nickel 60 nuclei, which remain with the still undecayed cobalt.
So is it clear now? The
Yes,
example I gave for carbon 14 is now given for the same way for cobalt 60.
hmm. I
So
mean, sir, does the cobalt, I mean, the half of cobalt 60 gets converted into nickel, and the nickel is like a part with the cobalt 60.
nickel, you see here we got here 8 gram, right?
Hmm.
At the beginning.
Hmm.
So it's converted to nickel, right?
Hmm.
And this nickel now 4 gram and cobalt 60 4 gram. We have
Hmm.
given there 8 gram total, right?
Hmm.
Uh, Now cobalt 60 converted to how much? It is converted to nickel. The rest part is still cobalt, and the part converted to nickel, that is nickel, right? But total
Hmm.
amount will be still 8 gram. Is it clear?
Okay. Hmm. Sir,
Cobalt
does
is,
the nickel
uh,
stay with the cobalt, or
yes,
does
it
it
is
like?
staying. It is staying, in mixture, right?
Okay,
Still,
okay, got it, got
it's
it.
in the
That must be.
mixture. It's not flying from there. Only
No, I
what
thought.
is happening? The emissions are, going away, right? The
Hmm.
the sample or the product, the given sample and the product, everything is staying together.
Okay, got
It's
it.
clear, right?
Hmm.
Okay. Now we are having the graph, this one, to understand half-life. You see, at the beginning, here we have time in the x-axis, and in y-axis we have the amount of radioactive material given. Huh? Maybe
Hmm.
the mass of the at the beginning of the radioactive sample is given A naught, right? Or the
Hmm. Like cobalt 60,
number of nuclei
4 8 gram.
is the number of nuclei is given A naught.
Hmm.
So after half-life, we are considering T as the half-life. Okay,
Hmm.
so after T, it will be A naught by 2. Then after
Hmm.
2 half-life, it will be A naught by 4.
Hmm.
And this way it will continue exponentially. Okay, exponentially it will continue. Is
Yes,
it
sir.
clear?
Okay. Hmm.
And the other definition we gave, there is another graph following that one. This one is related to the number of counts. The one I said you, number of disintegrations or number of counts, number of emissions, that one. Okay,
Hmm.
so this one you see, I'm making it bigger.
Sir,
Yeah,
uh,
now it's clear.
in the, yeah, in the curve, is it like the half life of this radioactive substance is 2 days, right? Because it is becoming 40.
Yes, 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 yes.
Right? Yeah, correct, correct.
It is showing the half-life is 2 days. So number of counts at the beginning, it was 80, right?
Hmm.
And the number of counts will be 40 after half-life, and the time required it is 2 days.
Hmm.
So another half will be it will be 20, right?
20 and four
Yeah,
digit index.
and you see, if you are drawing graph from 20, it will become here 4, right?
Hmm. Hmm.
And then 10, after 20 it is 10, it will become here, right? 6,
Hmm.
another half life.
Hmm.
Is it
So
clear?
it's not possible to be zero, right?
No, it will actually never possible to be zero. Uh, it's exponentially going. That's why it will be becoming very small, which is very close to zero. We can say it is
Hmm.
negligible, but we cannot say zero.
Okay.
So it's clear, right? And from
Yes.
those two definitions, the graph also given there. I think you understood. Now we are going to understand the hazards, radioactive hazards in our life, in animals' life, in plants' life, right? So
Yeah.
mainly we are focusing our lives, and directly or indirectly, if the plants or animals they are affected, then always we are also affected, right?
Hmm.
Because the animals we are having, if they are radioactive consumer, then they will, you see, the half life of carbon, half life. Just a minute, huh, Tamjid? Hello, Tamjid.
Yes, yes, sure.
I have a call here.
Yes, sir. No problem. No problem.
Okay, Tamjid, thank you for your patience. Now, what we are saying that Tamjid,
Yes, sir.
okay. So, what I was saying that if somehow any plant or animal or we are close to radioactive emissions or radioactive sample, then its effect is working for a long time, right? You understand from the half-life that if we have any uranium inside us, like any uranium sample inside us, then its radioactivity will work for generation after generation, right? Because
Hmm.
its half-life is very long. So we have to be careful about them, and as much as possible, we should avoid the radioactivity, right? Uh,
Hmm.
and what are the problems is causing, and how to avoid them, how to reduce the radioactive emissions. That one we are going to discuss now. Altogether, these are called radioactive hazards, right?
Hmm.
So you continue here, please. The effects of radiation on human body.
Uh, Radioactive materials are hazardous. Nuclear radiation can ionize atoms and molecules in the body, which may change the way cells behave. It can also transfer large amounts of energy into the body, which can damage or destroy cells. Effects that radiation has on human body include eye cataracts, cancer, skin burns, leukemia, and other blood disorders. Managing the risks. The risk associated with radioactive particles depends on the amount and type of radiation. For example, alpha radiation is more ionizing than gamma radiation but does not penetrate as far. In general, the dose received and the risk of ill effects increases by being exposed to highly radioactive materials, to radioactive materials for long period of time or on a regular basis.
Okay, then.
Precautions are taken to reduce the risk of harm when using radioactive sources. These include 5 points: keeping radioactive sources shielded when not in use, for example, in a lead lined box, wearing protective clothes to prevent the body becoming contaminated, limited exposure time, so less time is spent with radioactive materials, handling radioactive materials with tongs to increase the distance from them, monitoring exposure using detector badges, dosimeter.
Okay, so you understood, right? That
Yes, it's
it's very simple how to do this precautions, and you have to memorize all this. Sometimes it's coming in MCQ part, also in writing part. You have to write 3 points or
hmm,
2 points. Okay, those things you have to write nicely, uh, and that's why you have to memorize them, right?
hmm,
Okay, so radioactive hazards till here we are keeping now, and after that we are going to discuss background radiation. Okay, background radiation, then carbon 14 dating. Now it is 5:47, right?
hmm,
So we will have our discussion 6 from 6. Okay,
hmm,
another discussion we will have from 6 inshallah. Okay, the same password and ID.
okay, hmm,
I did not pray. I was waiting for you. Otherwise, I would go to the mosque. If I if I were known, then I could go to the mosque. Okay, thank you.
hmm. Okay, sir.